Hello everyone, welcome to my home, and today we're going over the first page of the second test on derivatives. So, we started off with a lot of words, but this one not so many words. Particle's position is given by x of t is equal to t minus a times t minus b. When is the particle at rest? Well, at rest we're talking about velocity. And we should know that the velocity of a particle is equal to the derivative of its position in terms of time. So we look at this. Oh, and there was the part I forgot to mention that tripped a couple people up who actually addressed this problem is that a and b are both constant. So we can treat them as numbers, just not numbers we know the identity of. So we're going to take the derivative. And so the velocity is equal to, this is a product rule problem, so it's the first times the derivative of the second, which is just 1, plus the second times the derivative of the first, which is also 1. So if we're talking about at rest, that means we want our velocity to equal 0. So 0 equals t minus a plus t minus b. A little bit of algebra later, we get that 2t equals a plus b, or that t equals a plus b over 2. I really want you to solve this one in particular because it's saying when we need a particular t value, and it's going to be the average of the two constants in this case, which you could have found without calculus if you had identified that this is a quadratic in factored form. Now, quadratics always have a form like that, and if it's in factored, it tells you where the two zeros are. So without loss of generality, we can say that one's A and that one's B. And if you know anything about quadratics in factored form, you know that the vertex, which is where the curve turns around, and so the velocity must equal 0, is going to be halfway between a and b, or just the average, a plus b over 2. Always be looking out for cases where you don't need calculus to solve it, because oftentimes it's easier. This one, we've got more words. The radius of a circle is increasing at a steady rate. So we'll take this first sentence and just, here's our circle. It has a radius. We'll call it r. Increasing at a steady rate, so the change in r over time is some constant, which we'll use k for that, for reasons that you'll see in a little bit. At a certain instant, the rate of increase of the circle's area is twice the rate of increase of the circle's circumference. So we're going to, again, digest that. The rate of increase of the circle's area, which we usually would say d area dt, is twice the rate of increase of their circumference. Just reading it as is, writing it as is. So what is the radius at that time? Well, we have a couple things. We need something that ties them together, and that's the fact that we know the formula for the area of a circle. That's area equals pi r squared. We know the formula for the circumference of a circle. That's circumference equals 2 pi r, so that the derivative of the area in terms of time, dA dt, is equal to, of course, 2 pi r dr dt. Derivative of the circumference, c dt, is equal to 2 pi dr dt. And so when you set these according to this bit of information together, we get that 2 pi r dr dt is equal to 2 times 2 pi dr dt. You notice when you set up like this, a lot of algebra happens. So we've got a pi on both sides, which we can get rid of by dividing both sides by pi. We can divide both sides by 2. We can divide both sides by dr t, and all we're left with is r equals 2. All right, it's amazing. And that is, what is the radius at this time? Well, it's 2. Moving on. We have the function g of x is continuous on the closed interval from 1 to 20 and differentiable on the open interval from 1 to 20, and has values given by the following table. Here's the table. You can read it yourself. Does g have a horizontal tangent line on the interval show? Justify your answer. Now, as you're reading this, since this is a problem made up by a person, kind of me, I got the form from an AP test, but I made up these values. When you read that a function is continuous on a closed interval and differentiable on an open interval, that should remind you, oh, there's one particular theorem that requires you to state that, and that's the mean value theorem. Which, let's remember, the mean value theorem says that, if you have a function that is continuous on closed, differentiable on an open, the average value, or the average slope, average rate of change from 2 points, so f of b minus f of a over b minus a is equal to the derivative at some point between b minus a, which we usually write it like this and let you remember things. So if we're looking for a horizontal tangent line, the horizontal tangent line, so I shouldn't have used f, I should use g. If it has a horizontal tangent line, that means g prime is equal to 0, right? So we just need to find an a and a b in the x's so that f of b minus f of a is equal to 0. We look up here and we see, oh, when x is 1, g is 14. When x is 10, g is also 14. So if b is 10, a is 1, there must be a value between 1 and 10. Let's call that value c, so that g prime of c equals 0 by mean value theorem. So g has a horizontal tangent line at c. Done. That's all you really have to say. Invoke that the mean value theorem applies and find a spot where there's guaranteed to be the average rate of change is 0. All right, now this is our related rates problem, our second related rates problem. We have a 5-foot tall woman is walking away from a 20-foot tall street lamp. So as you're reading these, you should draw a picture, and anything that stays the same, like the height of the street lamp or the height of the woman, you should label with what it is. So 20 and 5. Anything that's changing, for example, the distance that this woman is from the street lamp, you should draw that in, but you should give it a variable since it is changing. Let's call this L. We want to stay away from D. At a rate of 3 feet per second. So she's walking away at 3 feet per second. That means this distance is increasing at 3 feet per second. So we know that dl dt is 3. At what rate is her shadow lengthening when she is 15 feet from the base of the lamp? So let's draw in light from this lamp. It's the top of her head, casts a shadow on the ground. Here, from her feet to this top is the length of the shadow. We'll call that S. So we want to know ds dt. So the thing we're going to use here, and you can use other things, but this is the one that requires the least amount of outside variables, is we're going to use a similar triangle relationship. So we have this small triangle is similar to this large triangle. So we can set up a similarity ratio. We know that S over 5 is equal to S plus L. That's the corresponding long side on the bottom over 20. Now, if you take this, we could take the derivative implicitly in terms of time as it is right now. I'm going to do a little bit of algebra first because it's going to make things nicer. If we multiply both sides by 20 divided by 5 is 4, so 4s is equal to s plus L, which means that 3s is equal to L. Well, now if we take the derivative implicitly, well, the derivative of this side just becomes 3 ds dt, and this becomes dl dt. Don't know why I crossed the L, but that's okay. We know dl dt is 3, and so 3 equals 3 times ds dt, so our ds dt is equal to 1. If we want to put in some units, we'll say feet per second. It doesn't actually matter. We never actually needed this bit when she is 15 feet from the base of the lamp. Completely irrelevant in this case. Sometimes that happens. Sometimes you have extra stuff in the problem. No big deal. For t greater than 0, so we got positive t, particle's position is given by position, here we're labeling position as s, is equal to sine of t minus cosine of t. What is the particle's acceleration the first time the velocity is 0, right? So we got 2 bits of information we need to know. Well, just this first one here. The velocity, we of course know, is the derivative of the position. This one's pretty easy to take the derivative. That's just going to be the derivative of sine is cosine of t, and the derivative of cosine is negative sine. Then negative flips that to there. Okay, we need to set that equal to 0, which means that with a little bit of algebra, the cosine, we want a t where the cosine is equal to the negative of the sine. And we want the first time that happens. So there's actually an infinite number of times that this happens. We want the first time. If you go and look on your unit circle, cosine and sine are equal in magnitude at any of the pi over 4s. The first time where they're equal magnitude and opposite of sine happens here at 3 pi over 4. So we know that's the t we're looking for. Let's go back to the problem. What is the acceleration the first time the velocity is c? So we want the acceleration at 3 pi over 4. Well, the acceleration is the derivative of the velocity. We have our velocity here, so the derivative of cosine is negative sine. And the derivative of sine is cosine. Negative sine of 3 pi over 4, that's negative the square root of 2 over 2. Cosine of 3 pi over 4 is negative the square root of 2 over 2. Add these together and you get negative square root of 2. All right, moving right along. This is probably the most technical of this page. We are given an expression with dy dx in it, and it's implicitly, it's a relation rather than an expression. What is the value of the second derivative at 3, 0? All right, so the first thing we're going to do is note that dy dx is 2x minus y over x plus 2y, which if you plug in 3, 0, we get that is 2 times 3 minus 0 over 3 plus 2 times 0, which is just 2. Okay? that's a bit of side information. We're going to use that later, not quite yet. What we're going to do is we're going to take the derivative of this implicitly, and then we're going to plug in some values. So this is a product rule going on here. So we'll take the first, x plus 2y, times the derivative of the second. The derivative of dy dx is d squared y over dx squared, what we're looking for. Then we have to add the second, dy dx, times the derivative of the first. Well, that's going to be 1 plus 2 dy dx. That is equal to, derivative of that is 2 minus dy dx. Now we could spend a lot of time getting this in a nice pretty format with substitutions and all that jazz, but we have knowledge. We should use it. We know x is 3, y is 0, dy dx is 2. Let's go over here. We have 3 plus 2 times 0 times what we want, plus 2 times 1 plus 2 times 2 equals 2 minus 2. We're going to keep doing some stuff. Simplify, simplify, simplify. 0. 2 times 2 is 4, 5. That's 10. 10 plus 2 squared y over squared times 3. Some algebra happens, and you get that what we want is equal to negative 10 over 3. There you have it. Thank you for joining me. This has been really nice, and I hope to see you soon in class.